which specifically talks about the design of plastic sections. And we'll also be going to talk about what is plastic analysis, how plastic hinge is getting formed, what is plastic hinge. All these aspects we'll be talking in today's class. So we'll be covering the first part of the third unit in today's class. This one you can say. Okay. So before we talk about the terms of plastic or plastic analysis or plastic movement, let us understand what is a beam. So a beam is a structural member, as like columns or as like slabs, as like footings. We have beam as also a structural member, but the aspect of the beam is to carry the transverse loads. Okay, so a beam is actually a structural member which is subjected to transverse loads, or which is carrying the transverse loads. Now, what is transverse load? Suppose if you divide the loading pattern into two ways, very broadly, you have two types of loads. One is the axial load and the second one is the transverse load. Now, what is axial load? Any load that is passing through the center of gravity of a section. Okay, any load that is passing through the center of gravity of a section or through the axis of a section, then it is called as an axial load. So now what is transverse load? Transverse load is a load which is passing perpendicular to the axis. So you can see that very clearly in this figure. So consider this as figure 1 and this as figure 2. So in figure 1, you can see a column member is there. Okay, the thick color one, a column member is there. And you have the neutral axis or the centroidal axis, which is represented by the dotted line. And when a load P, okay, when a load P is passing through the centroidal axis of the section or through the center of gravity of the section, then it is called as an axial load. And the same load, when it is falling or when it is coming onto the member perpendicular to the axis of the section. Okay, you can see in the second figure. So in the first figure, the load, the axis is in this way and the load is exactly falling on the axis. Whereas in the second figure, you have the member in this way. That means you have the axis along the horizontal direction and the load is falling perpendicular to the axis. So this is what the axial load and transverse load. So majorly the beams will carry the transverse loads. So we know that beams are an horizontal members, and it is quite obvious that the maximum amount of loads on a beam will come in the direction opposite to the axis, right? So that is what the transverse load is. So in broadly, a beam is a structural member which is subjected to transverse loads. So transverse loads are the loads which are coming onto the member or which are falling onto the member in a direction perpendicular to the centroidal axis. That is what the transverse load on the transverse axis is. Now here, what happens when transverse load are coming onto the members? Consider here you have an I section. This is an I section pole and this is also an I section pole, right? So when transverse loads are coming onto the member, that is when the loads are coming perpendicular to the axis of the member, what happens is there is a chance that this member, right, the current poles, you can see the mode of deformation you can see here. So how does these current poles are getting deformed? They are getting deformed. Initially, they are in the perfect straight way, and you have the centroidal axis for this member. So when the load is falling perpendicular to the centroidal axis, what happens is this particular member will have a tendency to bend, right? So this is causing the member to deform or to change its original position, and you are also able to find certain kind of deformation, right? So this is what the transverse load caused to the any steel structural members. Now, in order to avoid this bending phenomena or in order to avoid this deformation phenomena, the best beam section is said as an I section. Okay, so if you are constructing the steel beams, it is advised to select an I section or I shaped section in order to cast a beam. And remember, here we are going to use the rolled steel sections or rolled beams, or we can also use the built up sections. It's up to us, or it depends on the conditions where we are going to use. Okay, so that's about the beams introduction. Okay, so a beam is a structural member which is subjected to transverse load, and the most economical sections for beam is a typical I section. Okay, now the next aspect is classification of steel beams. We have 6 to 7 different classification of steel beams that are available for us. Let's look at each one of these individually. So the first one is a floor beam or a roof beam, which are also called as joists. Okay, so a floor beam is a beam which is resting on the floor, and a roof beam is a beam which is above or which is resting just below the slab, or it may be sometimes inside the slab. So if you observe the figure here, this is the roof of the building, and just beneath the roof of the building you have the steel I beams. These are all beams, right? So these are called as roof beams. Suppose if this roof, whatever the roof that you're seeing here, the wooden roof, if this roof is somewhere below the beam, okay, then it is called as a floor beam. So the floor beams and roof beams, they are also called as joist members. So this is one of the classifications of steel beams. The second classification is girders. So technically these girders are again divided into two types. Okay, you have two broad classification of girders. One is a plate girder and the second one is a gantry girder. This will talk, a plate girder topic will be discussed in the 4th unit, and gantry girder topic will be discussed in the 5th unit. However, so what are these girders? Girders are very huge beams which carry excess amount of loads. Suppose if you want to construct a railway track, say for example you are going to construct a steel bridge wherein you are expected to have a railway track. So at those times, it is not just sufficient, or it is not just enough to provide just an I section or just a built up section. At those places where you are going to have expect huge amounts of loads, just the smallest possible I sections are not sufficient enough to take enough amount of loads. So at those places, you are going to provide a huge beams which are called as girders. So here in this diagram, the girder is this one. This entire portion is the girder. Okay, this we are going to design in the next unit, however. But remember, girders are very huge beams, and these girders are used when excess amount of loads are coming onto the members. And the girders are broadly classified into two types. One is the plate girders, and the second one is the gantry girders, right? So the next classification is the next classification is lintel beams. Now, what is this lintel? You all might be aware that a lintel is a support which is provided near to, or which is provided when you have openings in the structure. Suppose you have a window and you have a door, right? These two are the openings in a structure. So just above the window, you're going to place a beam which is called as a lintel beam. So if it is a concrete structure or if it is an RC structure, you're going to provide an RC lintel beam. And if it is a steel structure you are constructing, you are going to provide a steel lintel beam. But you have certain places where you can use, in the RC structure, you can also provide the steel lintel beam. So these things, I mean, the steel lintel beams are provided in the RC structures, especially when you provide shops or when you have shutters for a shop. You all know that shutters, right? So when you are providing the shutters to a shop entrance, it is mandatory to provide a steel beam, and these steel beams are provided just beneath the opening of the structure, and hence they are called as lintel beams. See here, you can see you have the brick wall. Okay, you have the entire brick wall which is provided here, and just beneath the opening, this is the entire portion of the opening. Just beneath the opening, you are provided with a beam which is a steel beam or steel I section, and this is called as a lintel beam. And here you have two vertical members. These are the steel columns. Okay, they doesn't carry any amount of load except the load that is coming from the steel lintel beam. Okay, this is what the lintel beam is. And the next category is purlins or rafters. So these are technically used in terms of trusses. Okay, when you have trusses in the section, or when you are constructing the trusses, It is mandatory to provide both purlins and rafters. We have the design of purlins in the fourth unit, in the fifth unit. So we'll be talking about these purlins very much detail in that particular unit. But however, purlins and rafters are provided in the trusses, and they are also acting as beam members. Okay. Now the next and the last one is the spandrel beams. Now what is this spandrel beams? Now observe this figure very carefully, the third figure. So here you have two different types of beams. One is you have the external beams. Okay, this is all the external beams which are provided at the corners, and you have one internal beam, right? You have one internal beam, and you have like 1, 2, 3, and 4 external beams. Whatever the beams that are provided at the outer face of any structure, remember, the beams that are provided on outer face of the structure are called as primary beams, and these primary beams are called as spandrel beams. Remember, for any structure you have two types of beams. One is the primary beams and the second one is the secondary beam. Primary beams are the beams which are provided along the outer surface of the structure or outer edge of the structure, right? So these primary beams are called as spandrel beams, and the secondary beams are the beams which are provided in between the primary beams. So suppose you have the primary beam 1 and you have the primary beam 2, right? In between these primary beam 1 and primary beam 2 are the external walls, or the external structures, or the external members. So if you provide any member in between these primary sections, then they are called as a secondary beams. Okay, this is also one of the types of beams. So these are the 5 broad classifications or 5 broad types of steel beams which we have. And now we look into the very broad aspects of the types of beams. We have 3 broad aspects. The first one is the universal beam, which is called as a rolled steel sections or rolled sections. So we have the ISMB, ISLB, ISWB, ISHB, right? So we have all the different types of I sections. So technically, if you are providing beams, they must be in the shape of I. Okay, and hence they are called as universal beams. If you are providing a beam in the shape of an eye, it is called as a universal beams, because these are the beams, or this is the shape which is universally accepted in if you are providing a beam members. Okay, so the first one is the universal beams, and which is most efficient in resisting uniaxial bending. And the second type of beam is the compound beams. Compound beams are also called as a built-up beams. That is nothing but you have an I section, and on the top flange and along the bottom flange, or maybe one of the flanges, you are going to provide a steel flat, that is ISF. You can see a steel flat that is provided on the top flange, right? So that is called as a compound beam, and these compound beams resist bending both in the vertical direction and in the horizontal direction. Okay, so these compound beams will resist bending both in the vertical direction as well as in the horizontal direction. And remember, these flats, that is the top plate which is provided on the top flange, can be provided either on the top flange and also can be provided on the bottom flange, and sometimes they can be provided on both the top flange as well as in the bottom flange. So this is what the compound beam is. And the last one is composite beam. So a composite beam is a beam which is a combination of a steel structure as well as the concrete structure. See, here you can see you have the steel I section which is provided, and you also have the concrete which is placing on the top of the member. So composite beams are the beams which are provided in conjunction with two different materials, that is a concrete material and also as a steel material. So these are the 3 broad classifications of beams. So first one is universal beam, which is a rolled steel section, and the second one is compound beams, or also called as built-up beams, and the third one is a composite beams, which is a combination of steel member along with the concrete member. So these are the 3 broad classifications of beams. Now we also have one more type of beam which is called as a castellated beam. Now what is this castellated beam? In castellated beams, if you if you remember very closely, in castellated beams, what happens is in the web portion of a beam, it is also an I section. Remember, castellated beams are also an I sections. In the portion of the web, what you are going to do is you are going to provide a diamond shaped holes. I'll show you the figure. See, you can see here. So in the web of the I section, you are going to provide the diamond shaped holes in such a way that it is proved that if you are providing a spacing, or if you are providing a vacant space or a hollow space in the web, these beams will have enough amount of strength to carry certain amount of loads. And remember, these cannot be used at all places. They can be used at the places where you are going to expect a very less amount of loads, but at a very frequent intervals of time, right? Remember, very less amount of loads and at a very frequent intervals of time. So those beams are called as a castellated beams. I'll show you a couple of more figures regarding the castellated beams. Yeah, so check this third figure. So you have the castellated beam. In the web portion, you are provided with a diamond shaped in the portion of the web, right? So these, in order to provide the castellated beams, it is suggested that ISWB are the most preferred sections. Indian standard wide flange beams are the most preferred castellated beams. And in this type, a cut is made in the web portion of the section. Why? It is because it is said that when the loads are very less and the frequency of the loads are very high, then at these places you can use these castellated beams. Okay. Now let's look at what are the different failure modes in the steel beams. So we have 5 to 6 different types of failure modes that are available for us. Let's look at each one of these. The first one is excessive bending. Due to excess amount of load, so what happens to the original section is it might get bent due to heavy amounts of loads. You can see the bending pattern here. So the entire beam has got bent in a very typical position, right? So this is one of the real-time examples of how a steel I section will get bent. And here you find the very excessive bending. So suppose you can say this is the normal position of the beam, and you can find the maximum deflection, the maximum bending, that is delta max, is very high. If this kind of beams are provided in the real-time scenario, obviously the failure is expected to be very high and the danger will also be very high. So this is one of the failure modes of beams. And the second one is the lateral torsional buckling. Now what happens in torsion? Torsion means, you have an idea, torsion is nothing but twist of the member, right? So sometimes there is a tendency that I sections may get failed due to torsion or due to twisting, and this twisting may be caused by the unequal distribution of the loads. Sometimes the twisting or the lateral torsional buckling will happen due to unequal distribution of the loads. So this is one of the other cases. And the third case is the local buckling. See, suppose if you observe this figure very closely, you have the initial position in this way. Forget about the bent position. So initially you have the perfect straight web, right? Now this local buckling is termed when you have the buckling is nothing but bending. When you have the bending only at a certain position, it need not be at the center, it can be at any portion of the section. Okay, it can be at any portion of the section. If you find the bending only at a particular span or only up to a particular distance, it is called as local buckling. We were talking about two types of bucklings. One is the local buckling and the second one is the global buckling. Global buckling is the buckling where you find the entire portion is getting bent, as you can see in the first figure, right? In the first figure, the entire portion of the structure has got bent, right? Whereas in the third figure, you are seeing only certain position or certain part of the section is getting bent, which is called as a local buckling. This is the third one. And we have three more types of bucklings or failure modes of the beam. One is the shear yield of web. So sometimes web will also get failed, which is in the form of shear, that is called as a shear yield of web. And the next one is web may suffer local crushing. That is, web may suffer local crushing. Here at these places, that the junctions of the flanges and the web, you are going to find that the web will get crushed. That is called as a local mode of the beam is buckling of flanges. So here you can see at a certain position the flange has got buckled and then it is perfectly straight. But whereas on the top flange it is normal. I mean it is quite good in condition. But only the bottom flange is has got bent up to a certain distance, and this is called as a buckling of flanges. So these are the different failure modes of a beam. Now let's look at the analysis of a beam. So how do we do the analysis of a beam? So broadly, we have two different types of analysis of beams. One is the plastic analysis, and the second one is the elastic analysis. Remember, the analysis of beams are broadly classified into two types. One is the plastic analysis, and the second one is the elastic analysis. Let's look at each one of these. What is plastic? Here we are not going to focus much about the elastic analysis. We'll be focusing only about the plastic analysis. Okay. Anyways, so let's look at what is this plastic analysis and what is this elastic analysis. Let's look at elastic analysis initially. You all know the elastic methods of deformation and the elastic analysis. Whatever you have performed in the structural analysis 1 and structural analysis 2, all those are elastic analysis, right? So what is this elastic analysis? An elastic analysis is performed by applying the design loads and required internal forces in the structural members are determined. Suppose you have a framed structure like this. Okay, you have a typical 3-bay, 2-story framed structure. Say, for example, you have this kind of steel structure. Okay, or it can be a concrete structure also. Anyways, so you have 3-bay, 2-story steel structure. Now, what will you do? How will you analyze this structure? You can analyze this structure by using different methods such as the moment distribution method, slope deflection method, conjugate beam method, unique load method, right? Stiffness matrix method. You have multiple methods to do the analysis of a beam. So what you are doing in analysis, what exactly you're going to find out? You're going to find out whether a particular joint is able to carry enough amount of loads or not. That is the first thing which you're going to find out. The joint, you can say it as a joint condition, right? Or the safety of the joint. So first one is you're going to find out the safety of the joint. Second one is if the joint is not safe, or if the joint is safe, you're going to find out whether the member is safe or not, whether the member is getting sway force or non-sway force. That also you're going to determine. And apart from that, you are also going to find out, suppose if there are any loads that are coming in the lateral direction, right? There is an obvious case that the sway will happen in the member, right? This is the entire analysis of a section. You're going to find out the loads and then you're going to analyze the member in such a way that whether the member is able to carry safe amount of loads or not, right? And also the end conditions are the safe conditions or not. Suppose sometimes you don't have, all the times you don't have the fixed support. Sometimes you might have the roller support, sometimes you have the hinge support, sometimes you have a combination of different supports. So you're going to analyze the member in such a way that whether the joints or the sections or the members of the section are safe enough to carry enough amount of loads or not. So this is what the elastic analysis is, which you have an idea. Now let's look at into plastic analysis. What happens in plastic analysis? Plastic analysis is defined as an analysis in which the ultimate load is the load which is considered in the design, right? Suppose if you remember the structural analysis concepts, you have, when you are doing structural analysis, suppose say for example you have a simply supported continuous beam which is carrying an UDL load. Say for example this beam is carrying 5 kilonewtons per meter of UDL load. Now when you're doing the slope deflection or moment distribution method or the conjugate, any type of the member, any type of analysis of the member, you never multiplied 5 with 1.5, right? You never have taken the factored loads, you have taken the design loads. That means whatever the load coming onto the member, you have taken the same load and you have analyzed the member. But what happens in the plastic analysis is you're going to consider the ultimate load. So how do you calculate ultimate load? When you multiply the given load with 1.5, which is a factor of safety, then you're going to get a factored load, which is also called as an ultimate load. So in plastic analysis, ultimate load is the major criteria which you are going to consider. But whereas in the elastic analysis, Just the design loads or the working loads are the loads which are considered in the elastic analysis. That's the key difference between elastic analysis and plastic analysis. Okay, so in elastic analysis, we are going to perform the analysis by considering the design loads or working loads. But whereas in plastic analysis, you are going to perform the analysis by considering the ultimate load or the factored load. That's the key difference between these two analyses. Okay. Now let's look at very broadly about the plastic analysis and the types of plastic analysis. Now, what are the different types of plastic analysis we have? We have three different types of plastic analysis. Sorry, not three, two different types of plastic analysis. First one is the static method. Now, what happens in the static method? So here in the static method, the first thing which you do after you are given a member, suppose you are given with a simply supported beam which is carrying a central point load. Just consider this way, a simply supported beam with a central point load. Now, what will you do? The first thing in the analysis part is you are going to find out the fixed end moments. After finding out the fixed end moments, you are going to draw the shear force and bending moment diagrams, right? You're going to draw the shear force and bending moment diagram. Now, after drawing the shear force and bending moment diagrams, what you're going to do is you're going to find out, suppose you have the maximum bending moment, right? The Mmax value is very high, then you will say that whatever the load that is coming onto the member, this load will make the structural to get collapse, right? So if the maximum amount of bending is happening to the member, this load will unstabilize the structure. That is what happens in the static method. And then whatever the load that is causing the collapse of the structure, it is checked that bending moment is not more than fully plastic moment at any section. Now, what is this fully plastic moment? Fully plastic moment is the moment which is available when there is a plastic hinge that is getting formed. I'll talk about plastic hinge a little later. But for time being, you just remember that what we do in the static method of plastic analysis is you're going to, after you are given with a problem, you're going to draw the bending moment for the structure. And then this bending moment diagram or this bending moment diagram is drawn in such a way that a mechanism is formed. Now, what is this mechanism? Mechanism is nothing but whether it is able to carry the loads or not, whether the shear force and the deflection values are within the limits or not, whether the fixed end moments are within the limits or not, whether the stiffness of the member is within the limits or not. All these things you are going to determine in the second step. Now, what will you do in the third step is you are going to find out what will be the maximum load that will cause a collapse of the member. That is what we are doing in third step. The collapse load is found out by working out the equilibrium equations. Now, in the next step, what you're going to find out is you're going to find out whether the bending moment is not more than the fully plastic moment or not. That is what the static method of plastic analysis is. Now we have the another method, which is the kinematic method. Now, what we do in kinematic method is initially we are going to find out all the plastic hinges that are formed on the structure. Please remember plastic hinges. This concept I will talk in the next slide. Initially in kinematic method, the first step what you do is you're going to locate all the possible places of the formation of the plastic hinges. Now in the next step, what you're going to do is the possible independent and combined mechanisms are ascertained. What is this independent and combined mechanism? Suppose at a particular joint, you have only the deflection, and at another particular joint, you have both the deflection as well as bending. At another particular joint, you have the deflection, you have the bending moment, and you also have the maximum shear force. So what you're going to do in the second step is you're going to find out what are the independent mechanisms and what are the combined mechanisms. Combined mechanisms are nothing but along with shear force, what else are also there, or along with bending moment, what else are also there. Independent mechanisms are nothing but you have either shear force or bending moment or torsion, or it can be of anything. So independent is nothing but if you have only one force that is acting on the joint or that is acting on the member, it is called as independent mechanism. Combined mechanisms are nothing but if there are any more than one mechanisms that are getting formed, that is called as combined mechanism. So you're going to find out the independent mechanisms and the combined mechanisms in the kinematic method. The third step, what you do is After you know the independent and combined mechanisms, you're going to use a method which is called as a principle of virtual work method. Okay, it is called as principle of virtual work method. Now what will you do by using this principle of virtual work method? You're going to find out what is the collapse load of the structure. Okay, so you're going to do the analysis by using a method which is called as principle of virtual work method. And here what you're going to do is you're going to determine what is the amount of load that is causing failure of the structure, which is called as a collapse load. So this is the third thing. And lastly, what you're going to do is you're going to draw the bending moment mechanism for bending moment diagram for independent mechanisms and for the combined mechanisms. For both you're going to draw, and you're going to ensure that bending moment is not more than the fully plastic moment at any section, right? Ultimately, both in the static method and in the kinematic method, your ultimate aim is to prove bending moment should not be more than the fully plastic moment, both in both the cases. Okay, but how to follow or how to determine this condition, we have different analysis. See, suppose if you do the moment distribution method or slope deflection method, ultimately you're going to find out the safety of the joints in both the methods, but the process of solving gets different. In one case, that is in the moment distribution method, you're going to draw the moment distribution table and then you're going to analyze, right? Whereas in the slope deflection method, you're going to find out the maximum slopes and the maximum deflections at a particular point. Ultimately, irrespective of what kind of structure you have, if you do analysis by any of the methods, they all will give you the same results. But how will you approach to the process of analyzing gets different. The similar way here also we have both the static methods and the kinematic methods. Both in these methods, your ultimate aim is to prove whether the bending moment is not more than the plastic moment or not. But the method of approach gets different. Okay, let's look at the plastic hinge capacity and what is this plastic moment and all. So now plastic theorems. We have three different types of plastic theorems. The first one is the lower bound theorem. Second one is upper bound theorem. And the last one is uniqueness theorem. Now what does these theorems have in common? So in lower bound theorem, which is also called as a static theorem or safe theorem, what happens is the working load will be less than the factored load. This condition is very important. W is nothing but working load and WC is nothing but the factored load. Okay, so in lower bound theorem, the working load is less than the factored load. But whereas in upper bound theorem, the working load is greater than the factored load. Okay, so this upper bound theorem is also called as kinematic theorem. And the uniqueness theorem is a combination of upper bound theorem and lower bound theorem. This is the key difference which you have to remember with upper bound and lower bound theorem. So what is this lower bound theorem is the working load will be less than the factored load, and in upper bound theorem the working load will be greater than the factored load. So these are the three different types of plastic theorems which you have. These are not there in your syllabus, but you try to remember what is this plastic theorems. If you know these, then it will be better to understand the plastic hinge capacity. Anyways, let's look at the plastic theory. Okay, so before we talk about all these terms, let's look at the stress strain curve of a mild steel. You all know the stress strain curve of a mild steel goes in this way. All right, you have the proportionality limit, elastic limit, upper yield point, lower yield point, ultimate load point, and breaking point, right? So this is the original stress strain curve of a mild steel portion. Now in plastic analysis or in plastic theory, what you're going to assume is some assumptions are there. What you're going to assume, the first assumption here is up to the first point. Okay, up to the point A, that is just before the upper yield point, what you're going to assume is this entire portion, whatever the curvature portion that is there, this entire portion is assumed as a flat portion. Okay, this entire portion is assumed as a flat portion. Now why we are assuming it as a flat portion is nothing but, suppose after applying certain amount of load, Okay, it reaches to a yield point, or it reaches to the limit of proportionality point. Now, even if you try to apply more amount of load to the limit of proportionality or beyond limit of proportionality, what happens is the member will tend to behave in a different pattern. That is, you have the lower yield, upper yield points, and then the ultimate point, and then breaking point. So ultimately, what happens is the failure of the structure is happening both in the assumed case and in the real case. So, but in the assumption case, or in order to do the plastic analysis, what you're going to assume is this curvature portion is not there in the section. You're just assuming it. It is not real, but you're just assuming. And then you are assuming that after reaching the maximum load, the member will not behave and the behavior will be linear. That means even if you try to apply the load, the member doesn't show any deformation, but at a particular point, the member will get breakdown. Okay, this portion is called as strain hardening effect. Okay, here you can see the first observation or the first assumption. So the strain hardening effects are ignored, and stress strain relationship is expressed through a two straight lines. That is, you have the first straight line and you have the second straight line. So this strain hardening point is ignored in order to analyze the member by using the plastic analysis. This is the first assumption. And the second assumption is that the effects of axial loads on fully plastic moment are ignored. Why we are excluding the effect of axial load? It is said that on beams you have only the transverse loads, you don't have the axial loads. So since you don't have the axial loads, you are going to avoid the effect of axial loads on the fully plastic moment capacity of a section. And the third assumption is the plane sections remains plane before and after bending. That you know, right? The plane sections remains plane before and after bending. And the fourth assumption is there is an identical relationship between the compressive stress, compressive strain, and the tensile stress and tensile strain. You know all these formulas. The compressive stress, which is stress equals to load by area, right? Strain equals to change in length by original length. And they said that they are going to assume that there is a constitutive relationship between the compressive stress, compressive strain, and the tensile stress and tensile strain. And the material is homogeneous. Okay, so that is also true because we are using only steel member. So entire beam is a steel section. So that means it's a homogeneous section. And the value of modulus of elasticity, that is capital E, the value of modulus of elasticity is the same in both tension and compression. So these are the 6 assumptions which we are going to do in the plastic analysis. Now let's look at what we are going to do in the plastic analysis. Okay, so this is what the stress strain curve of a mild steel. Suppose you take, see this is the UTM machine, and in the UTM machine you are placing a mild steel rod, right? Whatever you are seeing at the beneath the top and bottom, you are seeing a mild steel rod. So what happens? So up to proportionality limit or limit of proportionality, even if you try to elongate the member and if you remove the load, as soon as you remove the load, it regains its original position. That is what limit of proportionality is. And then the next step is the yield point. Forget about upper yield and lower yield point, just directly take it as yield point. Now what happens in the yield point is the material starts to behave or starts to lose its elastic nature and then attaining its plastic nature. Okay, that means if you try to release the load that is applied on the member, it does not come back to its original position. It takes some time, but it does not completely regains its original position. That is what yield point is. But ultimate point talks about, that is the maximum load a structure can carry or a member can carry. So here you can see both the upper yield points and the lower yield points are getting formed at the junction of the member. And ultimately you have the breaking point, which is called as a fracture point. Like this, you know, the typical stress strain curve of a mild steel. Now I said in order to do the plastic analysis, this entire portion will not be there. Okay, this is called as a strain hardening effect. The yield point, ultimate point, and the breaking point, all these 3 points are considered as a perfect straight line. Okay, anyways, we'll talk about this. So let's look at the plastic mechanism. Now in order to understand the plastic mechanism, let us consider a simply supported beam of length L, which carries a uniformly distributed load W. Okay, so please be very careful in understanding these concepts. So in order to define the plastic mechanism of a structure, what you're going to do is you're going to consider a cross section of a simply supported beam. Okay, a cross section of a simply supported beam where you have the uniformly distributed load W throughout the length L. Okay, now what happens if you are applying the load on this beam? So it behaves in these portions. So you have technically an I section. This beam, you can consider it as an I section beam. So you have the I beam on which you have the uniformly distributed load, okay, as shown in figure 1. So this entire thing you can take it as figure 2. Okay, now what happens here? Now within the elastic limit, okay, within the elastic limit, stress is directly proportional to strain. That means the stress is linear. You can see the stress is linear. Now here, as the load is gradually increased, remember very carefully, as the load is gradually increased, the stresses will also increase. Okay, as the load is gradually increased, the stresses will also increase till the extreme fiber is subjected to yield stress. Okay, as the load is gradually increased, so I'm increasing the load very gradually, and this happens till the extreme fiber is subjected to yield stress. Extreme fibers are these. So this is the extreme fiber on the top, and this is the extreme fiber at the bottom. So this happens till the extreme fiber is subjected to yield stress, which is called as Fy. Okay, so remember very carefully, I'll repeat the statements once again. You're going to consider a simply supported beam with a load W of uniformly distributed load, and within the elastic limit, the stress is directly proportional to strain. And as the load is gradually increased, okay, as the load is gradually increased, stresses in the member will also get increased. Okay, up to when the stresses get increased, up to till the extreme fiber is subjected to yield stress. These are the extreme fibers. Okay, till the extreme fibers are subjected to yield stress. So this is the extreme fiber, both in the top as well as in the bottom. Now, here you make sure of one thing. As you know that you are increasing the load gradually till the extreme fiber is subjected to yield stress. Now, even if you further increase the extreme load, okay, suppose say for example, here you are applying 10 kilonewtons of load in the first case, in this case. Okay, now in the next case, you are still applying some extra amount of load, which you can say it as 20 kilonewtons of load. Now, what happens here? Now, when you keep on increasing the load, okay, in order to simplify the analysis, let's look at this figure, that is the third figure. For simplicity of the plastic analysis, what you're going to do is stress strain curve of steel is assumed in this way. Okay, stress strain curve of steel is assumed as shown in the third figure. Now, what is this third figure talking about? It is talking about the limit of proportionality, and then the upper yield, and then the lower yield, and then a strike point. You are not finding the ultimate point and all, directly the breaking point, right? This is just for simplicity of analysis, right? So for simplicity of analysis, you are going to assume you have only the two lines. One is the linear line, which is in the inclined way, and the second one is the linear line, which is in the horizontal direction. Now, once you analyze the member, or once you simplify the section, what happens here is, if you keep on increasing the load, according to the theory of plastic analysis, the highly stressed fibers once yields, that means these ones, the highly stressed fibers once yield, that doesn't have any additional capacity to resist the loads. Okay, remember, understand very carefully this concept. So what we are doing in the first case is, in the first case, what you're going to assume is you have the UDL load, and this is the figure 1, you can say. Okay, I'll draw with another sketch so that it will be clear for all of you. Just a minute. See, in the first case, you have an I section which is carrying an uniformly distributed load. And on the I section, you are making certain amount of load is coming onto the member. Say, for example, it is 10 kilonewtons of load. Now, when you are applying certain amount of load, what happens is the extreme fibers, okay, the extreme fibers will reach to a value of Fy, that is yield stress. Now, even if you try to increase more amount of load, say for example, you are increasing 20 kilonewtons of load. From 10 kilonewtons, you are increasing it to 20 kilonewtons of load. Now, what happens here? Here, there is a peculiar phenomena that is happening. You can observe the thing very carefully. Up to certain extent, okay, up to certain extent, you are finding a rectangular portion in the member. Up to certain portion, you are finding a rectangular portion. After that, you are finding a linear portion, right? This is the entire linear portion. Now, the question is why this rectangular portion is forming on the compression zone and along the tension zone. It is because these fibers which are there, what are the fibers that are there in the rectangular portion, these fibers has reached their ultimate load point. Okay, these fibers which are there in the rectangular portion has reached their ultimate load. That means even if you try to increase any amount of load, these fibers which are there in the rectangular portion doesn't yield anymore. Now, in the third case, you are increasing the load to 30 kilonewtons. Okay, you are still further increasing the load to 30 kilonewtons. Now, what happens here? In this case, you can take this as second, third, and fourth figure. In the fourth figure, what happens is when you still increase the load, the fibers which are there in the rectangular portion, that is in this portion, that doesn't yield anymore. Okay, the fibers which are there in the rectangular portion, that doesn't yield anymore. Now, what are the fibers that are going to yield are the fibers which are not there in the rectangular portion. Okay, the fibers which are not there in the rectangular portion, these fibers will yield if you further increase the load. So that is what happened here. So if you're increasing the load to 30 kilonewtons, these fibers which are not there in the rectangular portion, they got yielded to a complete rectangular portion, right? They got yielded to a complete rectangular portion. Now, what happens when the entire section is getting yielded? Okay, or when the entire section is reaching to the value of Fy. Now, at this portion, what happens is there is a formation of a hinge, which is called as a plastic hinge. Okay, so now you might understand how the plastic hinge is getting formed. So the plastic hinge is getting formed in such a way that if you keep on increasing the amounts of load, if you keep on increasing the amounts of load on a particular member, when the extreme fibers in the compression zone and in the tension zone, when the extreme fibers or when all the fibers in the member, that is both in the compression zone and tension zone, will reach to yield stress. Okay, will reach to yield stress, then there is a hinge that is getting formed, which is called as a plastic hinge. Now, what happens after plastic hinge is getting formed? Suppose, say for example, here you have applied 40 kilonewtons of load in the fifth case. Okay, suppose in the next case, that is in the sixth case, you are applying 50 kilonewtons of load. Say for example, you have the sixth case also. In sixth case, what you have is you don't have the structure. The structure will get failed here. So once after the plastic hinge is getting formed, you should not apply any other further loads. If you try to apply any other amount of loads, the member will get collapsed. And that is what the plastic hinge is. So the plastic hinge is getting formed on the member when you have all the fibers in the compression zone and in the tension zone are reaching its ultimate loads, or reaching its yield stress values or Fy values. So that is what the concept of the plastic mechanism and the plastic hinge. Now you have another one which is called as plastic moment, which is called as MP. P represents plastic and M represents moment. Now, what happens in the plastic moment is just before the failure of the section, okay, just before the failure of the section, what happens is this portion which is there in the compression zone and this portion which is there in the tension zone will reverse their positions. Okay, that means this portion will come downwards and this portion will go upwards. That is what the plastic moment is. So moment is nothing but the twisting of the member, right? So this is the entire concept of plastic mechanism. So to brief this entire thing in a very simple terms, if you keep on increasing the load on a structural member or on a steel member, what happens is the fibers in the member will start to get yield. Okay, will start to get yield. When all the fibers in the member has started getting to yield, then there is a hinge that is getting formed, which is called as a plastic hinge. Even after the formation of plastic hinge, you are still trying to apply the load, then the structure will get failed. Just before the structure gets failed, what happens to the structure is the portion which is there in the compression zone will shift to the tensile zone, and the portion which is there in the tensile zone will shift into the compression zone, and then the failure happens. Once this shifting of compression and tensile zones is happening, the next and immediate phase is the failure phase. I'll show that in the real-time example case. See here, these are the three real-time figures which talks about the plastic hinge formation. See, initially there is a very small amount of deformation in the member, right? Both in the top floor and the ground floor. All right, this is the entire ground floor. Now, what happens here? Okay, in the figure one, what happens is when they are applying certain amount of transverse loads, or it can be any kind of load. Say here you can say it as a transverse load. When they're applying transverse load, what happens is the bending of the member is initially happening. You can observe that in the second figure very carefully. Okay, the deflection is very it can be seen with naked eye. In the first figure, the deflection cannot be seen. You have to observe in a very careful way. But in the second figure, the deflection can be easily seen in the figure. Now, what happens is the deflection happens when the extreme fibers. Okay, the deflection happens when the extreme fibers reaches its ultimate load or reaches its yield stress. Now, in the third figure, what exactly happening here is due to the formation of the plastic hinge. That means when all the fibers in the concrete or when all the fibers in the steel are reaching its ultimate position or ultimate load, then there is a formation of plastic hinge. Once there is a formation of the plastic hinge, there is a deformation to the structure or the collapse of the structure will take place. So now in the figures, you can see the plastic hinges are getting formed. See, this is a plastic hinge. You can see a mild cracks that are obtaining on the surface. Here also you can see a mild cracks. And then the failure had happened. Okay. Here you can see very carefully in the second figure, you can see a mild cracks that are happening on the member. And even if you try to increase heavy amounts of load, then the structure will get collapsed. That means whatever the moment that is there on the compression zone, it will shift to the tensile zone. And whatever the moment that is there on the tensile zone will shift to the compression zone. When these moments are shifting their places, then the collapse of the structure will take place. So that means initially wherever the plastic hinges are getting formed, at that place, the structure will get failed. So that is what the plastic hinge formation and plastic moment formation. Okay, so I hope it is clear for all of you regarding the plastic theory concepts. In the next class, we'll talk about the plastic moment and plastic moment capacity very detailed. Okay, this